Okay, so this supplemental video is made for lecture 19 when we talk about use chemical potential to explain one of the collective property, which is the non-volatile solute can increase the boiling point of water. Now, so in the class, what I did is I spent a little bit longer time to get everybody else to participate in the discussion. Now, in this video, what I will do is I'll basically compress all discussion into a little bit shorter video, so the video doesn't have to be an hour long. So, but it still capture the main point we have discussed. So I'll go through the main point and pretty much the same idea we have discussed, but it'll be largely focus on what I would just explain how we go about it. Now, so just to review a little bit on what we have discussed is that we used comparison between a pure water where you have water in the liquid case and water in the gas phase. So in this case, we express the chemical potential of the gas and the liquid using this little star. And then we have compared this with a situation where you have now water in the liquid. We are adding some solute, let's call B, and let's call this as a fraction B. So much so that the water's molar fraction is now become A. So this A basically refer as water for the moment. Okay, so we all know this is, since the solute is non-volatile, therefore it does not contribute anything to the gas phase. So the gas phase water is still pure. So here you got pure gas. Now, except the liquid water is now related to the pure state by the familiar formula we have discussed up to this point by the molar fraction of the drop. So, as we discussed in the class, we have explained because of now you can compare since the gas phase chemical potential still equal to this is the liquid. So therefore that means the gas phase of this solution of water will now be higher than the water in the solvent. So what I mean by that is to compare the system to the right, the chemical potential of gas, which is still pure, therefore it'll still be the pure water. So then, but now the water, the solvent water equals to the pure plus RT, this molar fraction. So that means for this part, the chemical potential of the gas minus chemical potential of the liquid. Basically, the gas is still pure. That means I don't write down the pure anymore, but I just talk about to the right hand side. And then you can substitute the pure to here, then these two will cancel. You'll get this formula as we discussed in the class. So that's what we arrived. So to make sure here we're talking about this can be either liquid or gas, because they're the same. So basically what we talked about this in the class is this is referring to the right side, the beaker, where the gas phase chemical potential is higher than the liquid because the molar fraction is always less than 1. This term is negative, the negative and negative will be positive. So this really means that the water in the solvent where other non-volatile solute is added will not be boiling at the normal boiling point because its chemical potential has been lowered by the non-volatile solute. Okay, so this is one point we have arrived through class discussion. Now the second point we have arrived in the class discussion is now we try to raise the temperature of the right hand side of the system so that we can catch the we can make up the difference of the of this chemical potential difference. So conceptually, we have used the idea that because to explain this point, we actually used this equation dG v dP minus dt. And if we're to talk about molar or chemical potential, we just simply add molar of each. Now we have explained in the class that for the gas phase, since now the pressure is fixed, so we can basically drop this term. So at a fixed pressure, so now we would basically now we can also replace this dgm. We kind of use the G molar or chemical potential interchangeably throughout this discussion. As you'll see, it'll become convenient, just so that for our own convenience, when we use something we are more familiar with before. Now, so we have sort of a qualitatively made argument. For example, for the gas, we have, for example, the chemical potential of the gas. Now here phase, it'll be the molar Gibbs image of the gas and dt, and for the liquid one, the molar entropy of the liquid and dt. Now, as we discussed in the class, our goal is we realize the chemical potential of the gas is higher than the liquid. Well, the liquid with the non-volatile solid in it. So the difference is that the gas chemical potential is higher than the liquid or the solvent, the solution, by this amount. So now what we have discussed in the class is that we can see at a fixed pressure, if we start to raise temperature, we can alter the chemical potential of the gas phase and the liquid phase, and both are dropping, except we notice that the molar entropy of the gas is always bigger than the molar entropy of the liquid in magnitude. So therefore, the chemical potential of the gas phase is going to decrease much faster as you change the temperature or raise the temperature to the right. So what this equation really tells us that qualitatively, by elevate the temperature, we will be able to find a new point where eventually the chemical potential will be below, either equal or below the liquid solution. So therefore, now all of a sudden the chemical potential of the liquid can start to be reaching to the gas, so it will be boiling again. So this is basically what we have ended in our discussion in the class. Now, what in this video, in the remaining of this video, what I want to do is I want to show you how we can quantitatively finish our discussion to show that how we can use these arguments, but then apply some mathematical tool to show that we can find a quantitative relationship as to what sort of, how do we relate the boiling temperature difference, basically the change of the boiling temperature, and the concentration of the solvent or solute. So this is what I want to do with this supplemental video to finish what we didn't have time to finish in the class. So before I get into more complex mathematical maneuver, I want to refocus what is the question we're trying to get at. So the goal here really is trying to relate the either the molar fraction of either the solvent or perhaps the solute to the changing boiling temperature, right? So that's basically what we want to do. Now, from the discussion to the left, we have already observed that when you have a pure system, you have chemical potential of liquid equal. When you have a mixture, you start to see where the gas is still pure, so therefore that's why the gas is still pure to the pure liquid. But except now the liquid is no longer pure, so that's why the liquid become deviate from the pure chemical potential by these terms. Now, as a result, the gas, well, this could be, since this gas is virtually just the pure, you know, or you can say the gas to the right side is actually still pure, so therefore it's still equal to that. Subtract this, and when you replace this term into here, this pure one will be canceled. That's how we got here. And we have used some reasoning in the class, as we discussed, that we know if we raise the temperature to the right side, we will be able to bring down the chemical potential of the gas phase. So we can actually eventually make the chemical potential of the gas phase to be equal or lower than the solution. Then all of a sudden the solution can start boiling again. Now, in the class, I was trying to demonstrate this idea. So I talked about the integration as we did it before. When we talk about the graphite diamond conversion, as we have seen in the one of the questions in the old exam. Now here actually turns out a much more convenient way to solve this problem is actually focus on goal. Our goal is trying to find out how much difference we can make by in terms of the temperature. Now one problem here is that as I actually some of you come to me, the challenging part is on the right side there's also a temperature term. Now the temperature is something we are trying to get at. So if we actually focus on this, is what we're trying to make up, which is I'm going to rewrite it over here. So basically, to the right side, the chemical potential of the gas is higher than chemical potential of the liquid by this amount, right? So that's basically the equation. Whenever we add some solute into the solution, and then we create a situation like this. So basically what we want to do is how do we start to change on both ends, and then we can start to make this left side to catch up to the right side. So that's the whole idea here. So so to actually do this, since we're going to just fix the pressure, we're going to change just the temperature. So, and that means we want to know how much change of temperature we can basically make up the difference. So that means it's much more, it's a mathematical trick. You don't want to have the temperature to be mixed up with the things you want to make up. So to really make this much easier to look at, you can just move the temperature to the left side. So you will have this is just kind of a mathematical maneuver. So you kind of move the RT to the left side. So you can just basically take the temperature to the left. So now you would have this situation. Now, so this here I have to use some kind of a sort of a mathematical scale to explain to you. So we have a functional to the left side, and the left side is what I want to know is I can change over the temperature. So every time I change the temperature, I can cause some change over this left function. Now that function should be corresponding to whatever the molar fraction I'm putting in. So that's also the change. So what I mean is that if you obviously when you this equals to 1, and then this gas will be pure, they will be pure, and then this height is 0, the left height is 0, everybody's equilibrium. So there's no difference. But as soon as I have some changing to the right, I add some small value to it, then the right hand side is no longer 0, And then the left side, of course, it's changing, but the left side I'm changing is I'm going to change the temperature. So so basically for every tiny X-ray, I can change a temperature. So that's the question, how do I do it? So how do I change the temperature to the left? So the left, if you actually look very carefully, virtually the left is basically, if you rewrite back, this may be confusing to you, but if I'm just rewrite the G molar of the gas, which is actually the chemical potential, and the G molar function of the liquid, and if I just write like this, you might actually realize this is something much easier to recognize, because this will just delta G vaporization, except it's a molar. So sometimes we use this a little tilde, or maybe we can just put molar here just so that you're familiar with it. And then if you actually write this way, then you probably know what to do, because you can say, oh, this is something familiar. Let me actually just write a little bit down here. So now then this really becomes just delta H vaporization minus T delta S vaporization divided by T, right? So once you have this, then you can actually rewrite this one more time. So this will become delta H vaporization minus T. Here, obviously, this will become minus delta S vaporization divided by R, because the T cancels, right? So this means the left-hand side really can be simplified as to two different terms. So what this really end up being is, you want to this term, of course, I'm just rewriting here, so I'm going to make a bracket. This should be equal to natural log XA. Okay, this board is kind of small, so I have to raise on the left side, and hopefully you can see also this is a change. Okay, so let me actually raise to the left side. Now we can have more room to work out the rest of this question. Okay, now what this expression really says is that because when we add some non-volatile solute, you caused the difference between the chemical potential in the gas phase and liquid phase, and the difference is by this amount. Or I can simply just rewrite this a little bit by saying the right-hand side here is that there is a function to the upside. This is actually related to the Gibbs the Gibbs energy change of vaporization. So you can actually write down them as 2 delta S vaporization divided with R. I could write down natural log XA. So that is the vaporization Gibbs energy divided by the RT, and this somehow this quantity represents the difference between the chemical potential of the gas phase and the liquid phase by that amount. So what does this really mean is that somehow we have to change T, so we can actually let this function to make up the difference, right? So that's basically what we want to do. So which basically what we want to do is we want change T so that delta H vaporization will become natural log XA. Now, but I'm not writing like this. This do not equal, because we know this is less than by that, but we want to change this over dt, and then times delta t. So that's basically the sort of a mathematical formula. So that should be natural log XA. So what does this really mean is that we want a range, like as I indicate to the right side, when XA equals to 1 and everything is equal. But when XA starts to shift into a new value, it's no longer 1. And then you will have a value to the right side. Then that's the difference caused between the gas phase and liquid phase when you add that. So what I'm doing right now, so for this is the difference I'm trying to make up. Remember, the difference is the negative natural log XA. Now, but I want to, what I want to accomplish is I want to alter the temperature of the left turn. So then they start changing value. Then the changing value of the left turn will start to compensate the difference of the log XA. So even though the equation here is in minus log, okay, so that's what I want to get. So if you actually, if this thing looked kind of hairy to you, strange, you think about this. You know, if I have a function that's this is the fx of that function. So you kind of like, so at certain point, I want to know a tiny changing of x plus delta x. So how much my change in fx would be like? So in this case, you just do something like you take a derivative, do the x, and then you take delta x. This is really what we're doing here. So what we want to do is we want to see how quickly this turn changing of the temperature. So we take a derivative of it. And then we basically either integrate over a temperature range. This I just approximately write down delta t here, but virtually this should really be a dt. So all really should be something like a integration. So after you take a derivative, and then integration at t be to a new boiling point. So you would put a bit dt over here. So basically that's what we try to do here. So let's just say first see what this thing looks like before I do the integration. So so what I'm basically saying is this is what I was trying to represent in here. So I'm taking these function to the derivative of the temperature, because x is equivalent to temperature. So the function basically is the Gibbs energy changing of vaporization. So if you so this is basically become a derivative taking process. So this is a totally constant because we are assuming the vaporization is a constant. This is a constant. So this term basically drop out, but and the vaporization of enthalpy vaporization also can be considered constant. So basically the left term become delta H vaporization and T. So this is just T minus 1, you minus 1 more to T minus 2, but because it's minus 1, you get a negative sign. So so this basically will become, now I'm already taking a gap of the dt. So basically you get for a tiny little temperature change, this basically that you can consider delta x to be very tiny. So this has to be integrated over a temperature, over a range to make up the total difference. So this is what we need to do, is we need to integrate this from T boiling point, a new point. So that's the sort of a complex concept here. So basically what this integration really will give us is it'll be something like, so this will corresponding to virtually the difference of natural log x 1, because T boiling point means we are molar fraction equals to 1, right? Minus, well, no, so the integration from boiling point to a new boiling point, the new boiling point basically is natural, you have the molar fraction A correspond to natural 1. That's right, so that's how the right hand side become 1 corresponding to when XA equals to 1. That's the pure, that corresponding to the boiling point. So now this left side integration basically become vaporization, and T boiling point 1 and T boiling point 1 equals natural log XA. Okay? Let me just run over room again. So notice that the negative sign disappeared because when you integrate a function at the denominator, and then the negative sign will basically go back with it. So basically this left-hand side would give you the formula that we will probably end up using. So basically here you would actually have vaporization and and times, so you can basically time this. So these two TB prime, they're pretty close. So but if you put this two together, it'll be TB prime, TB, then TB minus TB prime, log XA. Now, in this case, these two terms are similar enough, we can actually call them TB squared. And usually this is because the new boiling point is higher, so this will be a negative term. So we actually inversed it, so we can call delta vaporization. So basically this will be a negative TB prime minus TB, and then TB squared John log XA. So if we keep writing this, it'll become return more or less like this. Delta TB equals, and move the negative sign over here, natural log XA. Now, here in the textbook, the XA is a solvent molar fraction. You can always express them as a solute by 1 minus XB. So this could be written as minus natural log 1 minus XB. And then also in the textbook, you can see the in a math tool on the section 3.2, this term, when XB is really close to 0, so this is virtually minus XB. Now minus XB, this will be XB. So what does this really mean? We have accomplished the goal by showing that the change of boiling temperature when you add non-volatile solute in the solution will be equal to something TB squared delta H vaporization times the molar fraction of B. Okay, so what this is really mean is that I think I dropped something over here. I think the R is gone, so the R should have stayed here. That means, let me see, yeah, there should be R over here, there should be R over here, on top there should be another R. So what this whole practice is not trying to get you entangled with mathematical derivation. And the main point I want to sort of make here is that although the collective properties can be explained by qualitative rationalization or reasoning, as we did in the class, also the formula can be derived empirically. But if you dive into the principle of thermodynamics, and also if you apply some math skill, and you can actually use thermodynamics to prove that for a solvent or non-volatile solute added into solvent, you can cause the change of the temperature of the boiling point by a certain amount, and that certain amount can be related to the amount of solute you put in. So obviously in the equation you use to do homework, you have a constant, and some sort of constant that can empirically determine, and then you use a different concentration format. But obviously, you can see that what we're doing here is trying to show that the change of the boiling point can be related to the concentration of the solute added through a constant. So that's the whole point over here. Now, obviously, if you actually comfortable with all the derivatization process, that'll be very good. But other than to show the point that this is possible, but it's more important to show that the thermodynamics we have established can be used in other systems that's even more complex than what we have demonstrated here with collective properties. So the point is that later on we will actually use chemical potential, and perhaps in the future you'll use chemical potential in other systems. Then a lot of times with the proper mathematical tools, you can actually derive a lot more complex relationship that can be using chemical potential to explain many phenomena in both chemistry, chemical, and biological research. Okay, so before I close out, I just want to briefly review how we accomplish this demonstration. So basically follow the discussion we have done in the class. We have shown that when you add a solute in the solvent, you can cause the solvent's chemical potential to deviate from the pure form, pure liquid, by the molar fraction XA through this relationship, because in this case the gas phase is still pure. It's because it's a non-volatile, so there's nothing. It's only the solvent gas. So that's still pure. Where your chemical potential of the liquid become the pure, and then plus this. So when you subtracted the gas chemical potential to the liquid, then you would get this term. And then we have talked about this in the class, that this XA is smaller than 1, therefore this one is negative, and the negative of this is positive. The chemical potential of the gas phase is higher than liquid, so they cannot boil. Now, so what we want to do is we want to change the temperature to the system, so we can alter the difference of the chemical potential of the gas phase and liquid. And qualitatively, we discussed in the class that because we raise the temperature, we can lower the chemical potential of the gas phase faster than the liquid, because the molar entropy of the gas is higher than the liquid. So that's the foundation of this whole discussion. Now, also a little bit of strategic maneuver here is that we can focus on the temperature. So we move the temperature term to the left. Anything that has something to do with the temperature will to the left. So that's why we made this rearrangement. We move all of them into the left side, and then we kind of leave the molar fraction turn to the right. Now, and so what we're trying to restate in the problem is that when it's pure, the right side is 0, because that's 1. Then the gas with liquid is equal, the 0 equals 0, all good. Now, if we start to add a small amount of solute, XA start to deviate from 1, and then that's the difference of this. So the difference basically is the temperature. We want to know how the temperature alteration of the left-hand side can catch up of this difference. So before we do any further, we can just want to show you that what we are trying to change in. So the left term really is, so now we kind of, just try to get back to our familiar formula before, is we rewrite the difference, the chemical potential of the gas phase, the liquid, into molar Gibbs energy of the gas phase and molar Gibbs of liquid. So therefore, you can remember the delta Gibbs energy of the vaporization. We use the tilde, or sometimes we put the molar here to show that that's the vaporization of the Gibbs energy. Now, so when the delta G shows up, you can actually write them, delta H vaporization minus T delta S vaporization. Now, so this is the left turns. Basically, we rewrite these into something we're more familiar, and then we kind of continue write this. Now here, there's a little bit of tricky, because all we're showing here is that this left 10 is what the difference between the liquid chemical potential and the gas. So what we want to do is we actually want to change the temperature so we can make up the difference. So that's why the sign kind of changed a little bit. So we kind of want to alter this left turn here so that we can, how do we alter? We said, oh, we're going to fix the temperature, only change the fix the pressure, only change the temperature. So this is sort of a function. So think of it as fx. That's basically this whole term. And then the variable will change to the temperature. So if we were trying to observe a change of any sense like this, at a certain time point, a tiny little change of the variable, you take a derivative of this against that variable, and then you try to integrate over small range. In this case, use delta t. So the whole point is we want to make a change so that we can catch up whatever the difference of the earlier term we could not make, which is here. So that's basically the setup here. So now, so how do we do this? So you take a derivative to the left term against the t, which is the temperature we're changing. So the derivative, well, this is the constant that drops out. The t minus 1 becomes t minus 2, and then you get a negative sign over here. That's the derivative, and then the temperature over here. Now, but we're doing this, so this is basically the derivative, that is the dfx of dx, and then you do it. Obviously, if it's tiny dx, you just put a dx here. But if it's a delta x, you don't really do delta x like this. You integrate of td or tdb prime. So that's why this whole term becomes. So this left term really means that I'm going to change the temperature of this to the left side. And then this whole term is going to change by whatever this is representing. So the derivative dt integrating of range tb or tb prime. Now this has to equal to from the beginning, which is x equals to 1, and what I end up, which is natural log. This corresponds to tb prime, this corresponds to the beginning. That's the difference what I'm trying to make up. So this is the beginning, this is what I'm trying to alter the temperature. So then this will actually kind of provide to be to be equal to whatever the gap is. So this is not, then the rest of them is mathematical maneuver where when you integrate this in the t minus 2, and you integrate backwards, the next time is gone, so you basically have delta H vaporization over R, and here you will be 1 over T, or T over prime 1, the basic is just the integration to here. The right-hand side is just this is 0, so this becomes here. Now, the rest of them is just some mathematical maneuver. You combine two terms together. We take some assumption here. Because the boiling point change is so small, generally speaking, compared to boiling point, you can kind of take TB prime TB as TB squared. So we kind of approximate that. And also TB prime usually is boiling point. This is higher, so you don't take a negative term. So we actually flip them over to be TB prime has TB, so that's the delta TB. And here, the negative sign would actually come out because we just flip them over. Now, and then we used a little bit mathematical term here. That is, when you have a very small, we converted the XA into XB, and when the XB is tiny compared to 1, you go back to the reference in the textbook. Either we call it Taylor expansion. You can show that this term roughly equals to minus XB from this one. Here, then you can actually see the XB become, well, just this whole term will be approximately equal to XB. So then the delta TB, which virtually is the boiling point change, can be related to the molar concentration of the solute by RT squared, delta H vaporization. So the left-hand side, for the most situation, when we deal with the small, they can consider the constant. So this whole idea is trying to show you the empirically determined relationship, that is the boiling point elevation to the solute concentration can approximately be a linear relationship, and something that we can explain using thermodynamics. So that is the empirical observation can be proven by thermodynamic argument. So that's the whole idea here.